The problem that we are going to solve today is possibly my favorite problem for illustrating the concept of states. This is hidden path. The problem goes like this. We are given a pattern like this one over here and also a matrix like this one over here. The matrix represents a maze where the one in the first row is the entrance of the maze and the one on the last row is the exit of the maze. The problem is to write a program that reads the matrix and the parent and finds a path from the entrance to the exit. And the path must fulfill the following conditions. The path must match the pattern over here, even if it's repeated from the beginning until the exit. For example, this is a possible path. 1, 3, 5, 8, 3, 5, 8, and 3, and it finishes here. The matrix can be as big as 300 by 300, and the pattern can be as big as 50. And also the path found should be the shortest one that fulfills the restriction. If you need more details, I leave a link on the description below with the full description of the problem. As always, I encourage you to try to solve this problem by yourself first and pay special attention to which part of the process you struggle in order to restructure your way of thinking for solving the next problem. If you want to attempt to solve this problem without any hint, pause the video now. Some people may be tempted to define the state space as pairs of rows and columns. Let's see an example where this approach fails. Here, take a look at this case over here. Here, the red path cannot go left, cannot go to the 2, because the next number in the pattern is another 3. But the blue path can indeed go to the 2 because it's 2, 3, 4, 3, 4, and the next number should be a 2. So just the row and column is not enough to define the state here. There is something else needed to fully describe the restriction. And also, if you notice, it can make sense for the path to cross by itself. Check here, for example, with the red path. It can go here to the 3 and then go back to 4. So it can continue to the 2 and then to 1 and finish. As we have done it before, let's reframe this problem as a sequence of choices and also restriction. At any moment, the choice is always to move in one of 4 different directions. So every sub-solution could be fully described by a vector of direction indicating which path is being followed. The next thing that we have to do is to consider the set of restrictions. Let's summarize them. One of them is that you cannot move outside of the grid. And the second restriction would be that the numbers along the path should match the numbers in the repeating pattern. I hope it's clear with the two restrictions that they fully represent how the path should be in order to fully solve the problem. But we need to rephrase these restrictions in order to be able to program them, so let's express them mathematically. First thing first, the variable name. Let's call RC to the current position on the matrix, that is row and column. And now let's call K to the number of steps that we have done it so far. Then the same two restrictions mentioned previously can be rephrased mathematically like this. Here is you cannot move outside the grid, and this is that the number on the matrix matches the number on the pattern. Then if we recall the search tree with all the sub-solutions, that is a tree that represents all the possible paths on the grid, we want to know when two of these branches are identical. And I claim that the branches are identical when they represent a path that reaches the same place, the exact plane, and also the index in the pattern is the same. And with index in the pattern, that can be computed with the length of the path module P. That is, if these three variables or these three expressions are the same for a particular sub-solution that corresponds to a particular vertex on the search tree, then the branches below them would be identical. Proof would be just take another look at the restrictions, and here the restriction depends on these two variables R and C, and for this expression the remainder of A model P. And the size of the state space would be at most the number of rows times the number of columns times the size of the pattern. So this is the maximum number of rows, the maximum number of columns, and the maximum length of the pattern. Perfectly feasible for solving this problem. So let's draw a diagram of the state transitions in the same way that we have done it before. This would be the diagram for the state transitions. This would be the actual state or the current state, and this other state would be the state where it's possible to move to. Then with this diagram in mind, we should be able to deduce the recurrence, right? Wrong. What's the problem here? There are cycles. In a problem that we solve using the recurrence or a memorization, we cannot allow these kind of things to happen. So we have a set of states and a set of transitions of states, and we want to find the path from a start to an end, minimizing the number of transitions along the path. I wonder if there is already something to do that. It's a breadth first search. It may seem odd to use breadth first search in a dynamic programming tutorial, but remember, dynamic programming is being able to split the main problem into overlapping subproblems, and this is very present here. Also, the most important lesson here is the reasoning for solving the problem by finding its states. Not if we end using breadth first search or a memorization or a couple of nested loops. All the trick here is just use these tuples over here to represent node in a graph, and then use that for breadth first search. You don't even need to create the whole graph in order to do the breadth first search traversal. This is the code for solving the problem. The state that you can see is represented by three numbers: row, column, and index. Then we use a queue of states starting to row 0 and the position of a 1, and the index 0, and this code over here is the breadth first search. If you already know breadth first search, I think this should be self-explanatory. If you don't know it, then I think you should check breadth first search before attempting dynamic programming. Here, every state is visited at most once, and also each visit of a state that is distinct takes constant time. Here it's a loop, but it iterates a fixed amount of time. It's just the 4 directions defined here. Then the time complexity of this is the size of the matrix, that is n squared, times the size of the pattern, that is p. And also the memory complexity is the same. This is all for now. I hope this is useful for you. If you have any questions, don't hesitate to leave them in the comments below, and keep practicing.